8362. What effect, if any, does altitude have on VMC for an airplane with unsupercharged engines? A. None. B. Increases with altitude. C. Decreases with altitude. The correct answer is C. VMC is the airspeed at which the airplane achieves the greatest altitude gain per unit of horizontal distance traveled. As altitude increases, the air density decreases. With lower air density, the airplane's wings generate less lift, requiring a higher indicated airspeed to maintain the same lift and climb performance. Therefore, as altitude increases, VMC decreases. This means that the airplane needs to fly at a lower airspeed to achieve the best angle of climb performance at higher altitudes. 9813-1. High-density altitude can reduce turbojet aircraft performance in which of the following ways? A. It reduces the likelihood of maintaining laminar flow over the airfoils as airspeed and altitude increase. B. It reduces thrust because there is a reduced mass of gases to force out of the exhaust. C. It reduces thrust because there is an increased mass of gases that inhibits the outflow of exhaust. The correct answer is B. When air density is reduced, the engine's compressor section has to work harder. At high-density altitudes, power capacity decreases and potential power utilization must be regulated to maintain engine temperature within acceptable ranges. 8363. Under what condition should stalls never be practiced in a twin-engine airplane? A. With one engine inoperative. B. With climb power on. C. With full flaps and gear extended. The correct answer is A. Stall practice in a twin-engine airplane should never be conducted with one engine inoperative. This is because stalling a twin-engine airplane with one engine inoperative can lead to an uncontrolled spin or loss of control, which can be extremely dangerous. During a stall, the airflow over the wings becomes disrupted, and the lift generated by the wings decreases significantly. In a twin-engine airplane, stalling with one engine inoperative can cause an imbalance in thrust, yaw, and roll, which can lead to an asymmetrical stall and a loss of control. When an engine is not operating, the remaining engine's thrust and the control effectiveness may not be sufficient to counteract the adverse effects of the stall. The airplane may enter into a spin or experience uncontrollable yaw, making recovery difficult or impossible. Therefore, it is crucial to follow appropriate procedures and guidelines provided by the aircraft manufacturer and aviation regulatory authorities regarding stall practice in twin-engine airplanes. 8349. If no corrective action is taken by the pilot as angle of bank is increased, how is the vertical component of lift and sink rate affected? A. Lift increases and the sink rate increases. B. Lift decreases and the sink rate decreases. C. Lift decreases and the sink rate increases. The correct answer is C. As the angle of bank increases, the total lift generated by the wings is divided into two components: the vertical component, lift, and the horizontal component, centripetal force. The vertical component of lift decreases as the angle of bank increases. This reduction in lift means there is less force available to oppose gravity and support the weight of the aircraft. Additionally, the sink rate increases as the angle of bank is increased. The increase in sink rate means the aircraft descends at a faster rate per unit of time. This happens because the reduction in vertical lift component decreases the upward force that counteracts the downward force of gravity. Therefore, as the angle of bank increases without corrective action, the vertical component of lift decreases and the sink rate increases. 8350. Why must the angle of attack be increased during a turn to maintain altitude? A. Compensate for loss of vertical component of lift. B. Increase the horizontal component of lift equal to the vertical component. C. Compensate for increase in drag. The correct answer is A. During a turn, the angle of attack must be increased to maintain altitude. Option A correctly explains the reason for this adjustment. When an aircraft is in straight and level flight, the lift generated by the wings is primarily directed vertically, opposing the force of gravity and supporting the weight of the aircraft. However, when the aircraft enters a turn, the direction of the lift vector needs to be adjusted to counteract the centrifugal force that tries to pull the aircraft outward. In a turn, the horizontal component of lift is responsible for providing the centripetal force necessary to keep the aircraft in a curved path. This horizontal component of lift contributes to changing the direction of the aircraft's velocity vector, allowing it to turn. To maintain altitude during the turn, the vertical component of lift must remain sufficient to counteract the force of gravity. Since the total lift force is divided into both vertical and horizontal components, increasing the angle of attack increases the vertical component of lift, compensating for the loss of lift due to the change in direction.